So we've been talking about heat engines, and we talked about efficiency, where we know that the thermal efficiency is the energy benefit divided by the energy cost. That's going to be the net power divided by the heat in, or if we do some manipulation, 1 minus the heat out divided by the heat in. But for Carnot engines or ideal engines, then we see that we can replace this ratio of heat transfer rates with a ratio of temperatures. As long as we remember to use absolute temperatures here, we'll get the right answer. So now we're going to do a heat engine example. And this heat engine looks like this, which is kind of a basic coal-fired or nuclear-fired power plant. What we're asked to do is find the actual thermal efficiency here, given the different state points that we have, and then compare that to the Carnot efficiency. So we'll be using both versions of the thermal efficiency equation here. Right now, when I look at this state table, I can see that I know two things about state 1. So this is a saturated vapor at 300 degrees, so I can fill in my state table. And state 4, I can also fill in my state table because I know two things about that state as well. So even before doing any of the problem, I can get some data that I figure I'll need as we move through the problem. I can also draw the processes involved in this heat engine on a TS diagram. First, I'm going to boil the water in my boiler. Here, I'm told that I go from a saturated liquid to a saturated vapor at constant temperature. Now, I'm going to assume that this turbine is an ideal turbine. And if I can make a series of assumptions, I see that that ideal turbine ends up also being isentropic, so that the specific entropy at the inlet and the outlet are the same. So this is a vertical line down. Then I condense the fluid so that it's mostly liquid. You wouldn't do it this way in a real problem. But in this case, I want to be able to keep the temperatures the same as I'm adding and rejecting heat. So we're going to cool this down till it's mostly liquid. And then we're going to run through an ideal pump, which again is a vertical line because it will be isentropic. So this is what the TS diagram of this particular heat engine looks like. I'm adding heat between state 4 and state 1. I'm generating power between state 1 and 2S. I'm cooling my fluid between state 2S and 3, and then I'm adding power in between state 3 and state 4S. My thermal efficiency is going to be the energy benefit divided by the energy cost, or in this case, the power, the net power produced by the heat engine divided by the heat transfer rate in. My net power can be my turbine power plus my pump power divided by the heat added at the boiler. Now here, I add these two things together because I don't use absolute values. I use the first law and I let the sign tell me whether I'm adding work or taking it away. And that means I have to add these two values together, which looks a little different than what you might see in the textbook. I don't know the thermal efficiency. I don't know the turbine power or the pump power or the heat rate in. So I got to do first laws on all of these components. Let's look at the turbine and the pump. Here I make the assumptions that I usually make for these components, and I'll get the expression for both of these components that power is m dot times H in minus H out. Now again, we're expecting the turbine power to be positive and the pump power to be negative, but I got both of these expressions from the first law. Now I want to find an expression for the heat that I'm adding through the boiler. Again, I'm going to make a series of assumptions and manipulate my first law so that here I get an expression that this heat rate in at the boiler is the mass flow rate through the boiler multiplied by H out minus H in. So now I've got an expression for my thermal efficiency. I don't know any of these mass flow rates. I found H1 and H4, but I don't know H3 and H2. So let's start by looking at the mass flow rates. If I do conservation of mass on all of these components in the system, they're all steady state and they're all one inlet and one outlet. What that means is that the mass flow rate through all of these components are the same, and they're lined up in series, and we just keep going around and around in the cycle. So there's only one mass flow rate in this problem. And what that means is that all of these mass flow rate terms are the same. So every term is multiplied by the mass flow rate here. So I can cancel the m dot term out. And now the only thing I need to find the thermal efficiency is H2 and H3. So how do I find those? As I go through my ideal turbine, from my second law analysis, if I make the assumptions that the system is at steady state, that it's adiabatic, and that it's one inlet and one outlet, and that the turbine is ideal, then I'll find that the specific entropy at the end of the turbine at state 2 is the same as the inlet. This is an isentropic turbine. So now I know the temperature and I know the specific entropy. When I drew this out, it was under the vapor dome, so I can look at table 2, A2 in the textbook, and find the quality and the specific enthalpy. If you want to see these things calculated, check out the long version of this lecture. We can do the same thing for state 3, recognizing that it's the pump that's isentropic here for the same reasons as the turbine, so that S into the pump must be the same as S out of the pump. Again, here I know the temperature, so I can fix the rest of the states. So now I have a lot of information that I can put into my calculator. All of these H terms are in kilojoules per kilogram, so the units are the same in the numerator and the denominator, so they'll cancel out, which is what we're expecting, because here we're expecting an efficiency. It should be a number between 0 and 1, and it is. And if I multiply by 100%, I see that my thermal efficiency is 50.6%, which means about half the heat that I put into my engine end up turning into work. Now, if I assumed right from the bat that this was a Carnot engine, what would happen? So I've assumed that all of the components in my system are ideal. None of them are generating entropy. And my heat addition happened at constant temperature, and my heat rejection happened at constant temperature too. So now I can see that this thermal efficiency for a Carnot engine is 1 minus T out over T in, which is T cold over T hot, because I reject heat at the cold place and I add heat at the hot place. Now I have to remember not to use these temperatures as Celsius or Fahrenheit. I have to use Kelvin or Rankine. So I use absolute temperatures here. I add 273 to both my numbers, and I get a thermal efficiency. And in this case, because all of my components were ideal, I get the same answer that I did when I analyzed this system component by component. So it's worth remembering we can only use this equation, right, this strategy, when we have an ideal engine. But the other strategy we had, going component by component and determining the net power and the heat in, we can use that every time for a heat engine. So that's it for thermo shorts. I'll see you again next time.